Everything dies. Stars die. Planets die. Galaxies, given enough time, will come apart at the seams. Even black holes, the most permanent-seeming objects in the universe, will eventually evaporate into nothing. This is not speculation, this is physics. But the universe itself, the entirety of space-time, the fabric that holds everything, the stage on which every event in cosmic history has ever played out, can that die too? And if so, how and when? The answers that science has found are, I think, the most beautiful and the most devastating things humanity has ever discovered. To understand how the universe will die, you need to understand entropy. Entropy is a measure of disorder, a measure of how spread out energy is. And the second law of thermodynamics, one of the most fundamental laws in all of physics, states that entropy always increases. Energy always spreads from concentrated to diffuse. Hot things cool down, structures fall apart, order becomes disorder. This is not a tendency, it is a law, and the universe obeys it without exception. Right now, the universe is young. It is only 13.8 billion years old. Stars are burning, galaxies are colliding, new stars are forming from clouds of gas. Energy is concentrated in dense, hot, active structures. Entropy is still low, relatively speaking. The universe is vibrant and alive with activity. But it will not stay this way. We are currently living in what cosmologists call the Stelliferous Era, the age of stars. It began a few 100 million years after the Big Bang, when the first stars ignited, and it continues today. This is the era of everything familiar.
The sun, the planets, the Milky Way, every galaxy you have ever seen in a photograph, all of it exists within this one brief cosmic chapter. And I want to be honest about something that took me a long time to accept. The Stelliferous Era is not normal. It is an anomaly, a brief window of light in what will be an almost infinite duration of darkness. The universe will spend the overwhelming majority of its existence in states where no stars shine, no planets orbit, no light crosses the void. The age of stars is not the story of the universe, it is the prologue. The Stelliferous Era will end in roughly 100 trillion years. That sounds like a long time, and in human terms it is incomprehensible. But on the scale of the universe's total lifespan, it is the blink of an eye, a candle flame compared to the darkness that follows. Here is what happens. In roughly 4.5 billion years, the Milky Way galaxy will collide with the Andromeda galaxy. The two spirals will merge over hundreds of millions of years into a single giant elliptical galaxy that astronomers have already named Milkdromeda. This collision will trigger a burst of new star formation as gas clouds smash together, but it will also mark the beginning of the end. The merger will consume much of the remaining star-forming gas, accelerating the depletion of the raw material that stars need to be born. And the expansion of the universe will have pushed most other galaxies beyond our cosmic horizon. A few trillion years from now, an astronomer in Milkdromeda, looking up at the sky, will see nothing more than their own galaxy. Every other galaxy will have receded so far that its light can no longer reach them. The cosmic microwave background will have been stretched to wavelengths so long it becomes undetectable.
Future civilizations, if they exist, will have no way of knowing the universe ever contained anything beyond their own island of stars. The evidence of the Big Bang itself will be erased. Star formation requires hydrogen gas. Clouds of hydrogen collapse under gravity, heat up, and ignite nuclear fusion. That is how every star that has ever existed was born. But the supply of hydrogen is finite. Each generation of stars converts hydrogen into heavier elements, and the expansion of the universe pushes galaxies apart, cutting off the supply of fresh gas. Over trillions of years, the gas runs out. Fewer and fewer stars form. The ones that exist burn through their fuel and die. The most massive stars die first. They live fast and burn bright, exhausting their fuel in a few million years and exploding as supernovae, scattering heavy elements across space. Medium-sized stars, like our Sun, live longer, roughly 10 billion years, before swelling into red giants large enough to swallow their inner planets, then shedding their outer layers in glowing planetary nebulae, leaving behind white dwarfs. The smallest stars, the red dwarfs, burn their fuel so slowly that they can last for trillions of years. A red dwarf born today will still be shining long after our Sun has been dead for 90 trillion years. These tiny, dim stars, some no larger than Jupiter, will be the last to shine, the last sentinels of light in a darkening cosmos. Our own Sun will die in roughly 5 billion years. It will exhaust its hydrogen in its core, swell into a red giant large enough to engulf Mercury, Venus, and possibly Earth, then collapse into a white dwarf about the size of our planet, but with the mass of a star. Over billions of years, that white dwarf will cool and fade, becoming a black dwarf, a cold, dark, invisible sphere drifting through space. Every star you can see in tonight's sky will eventually share this fate, or something like it. And when the last red dwarf finally exhausts its hydrogen and fades to black, the Stelliferous Era is over. The universe goes dark. I find this image unbearably sad, not because it happens quickly, because it happens slowly. The lights go out one by one over trillions of years. Each star that dies is not replaced. Each galaxy gets a little dimmer. The night sky from any point in the universe gradually empties. The last star does not explode dramatically. It simply fades, a tiny red ember growing dimmer and dimmer until it is indistinguishable from the void around it. And then, silence. What follows is the Degenerate Era. It lasts from roughly 10 to the 15th power years to 10 to the 39th power years after the Big Bang. The universe is now dark. No stars shine. The only objects remaining are stellar corpses, white dwarfs, the cooling remnants of sun-like stars, slowly radiating away their stored heat over billions of years until they become black dwarfs, cold, dark, invisible spheres of carbon and oxygen floating through the void. Neutron stars, the ultra-dense remnants of massive stars, gradually cool and spin down. Brown dwarfs, objects too small to ever ignite fusion, drift through the darkness, slowly cooling. Occasionally, two brown dwarfs might collide and briefly produce enough mass to ignite fusion, creating a new star for a short time. But these events are extraordinarily rare, perhaps once every quadrillion years in a galaxy the size of the Milky Way. Brief flickers of light in an ocean of darkness. And the galaxies themselves are coming apart.
Over immense timescales, gravitational interactions between stellar remnants gradually eject some objects into intergalactic space, while others fall toward the supermassive black hole at the galactic center. The galaxy dissolves, its components scatter. But even the dead stars do not last forever. If proton decay is real, and many theories in particle physics predict it is, then the protons and neutrons that make up all ordinary matter will eventually fall apart. The half-life of a proton is predicted to be around 10 to the 34th power years. That means after roughly 10 to the 40th power years, virtually all ordinary matter in the universe will have decayed into subatomic particles. White dwarfs, neutron stars, planets, everything made of atoms, dissolved at the most fundamental level. Not broken apart by force, dissolved by time. And that thought genuinely unnerves me. Not just that everything ends, but that matter itself is temporary. That the atoms in your body, the atoms that have existed since they were forged in ancient stars, are not permanent. They are borrowed, and the universe will eventually take them back, particle by particle, over timescales so long that the current age of the cosmos is a rounding error. After the death of matter, only black holes remain. This is the black hole era. It lasts from roughly 10 to the 40th power years to 10 to the 100th power years after the Big Bang. A Google years.
A 1 followed by 100 zeros. Black holes are the last structured objects in the universe. The supermassive black holes that once anchored galaxies now drift through a void that contains almost nothing else. They are the universe's final monuments. But even black holes die. In 1974, Stephen Hawking proposed that black holes are not truly black. Quantum effects near the event horizon cause them to emit a faint glow of radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to lose mass. Slowly, unimaginably slowly. A black hole with the mass of our Sun would take roughly 10 to the 67th power years to evaporate. A supermassive black hole might last 10 to the 100th power years or more. To put that in perspective, the current age of the universe is about 10 to the 10th power years. A googol is 10 to the 100th power. That means the last black hole will survive for a period of time so long that writing out the number of years would require more zeros than there are atoms in the observable universe. But eventually, even the largest black hole in the universe will shrink. Its event horizon will contract. As it loses mass, its temperature actually increases. A dying black hole gets hotter as it gets smaller, the opposite of what you might expect. In its final moments, the temperature skyrockets and the black hole emits a burst of particles and radiation in one last flash of energy before vanishing completely. The last black hole in the universe will be the last structured object to exist. When it evaporates, it releases a brief flash of particles and light into the void.
For a fraction of a second, there is light again in a universe that has been dark for longer than any number you have ever conceived. And then it is gone. The last thing in the universe, gone. After that, the cosmos enters what physicists call the dark era, a universe of near absolute emptiness. Only photons, neutrinos, electrons, and positrons remain, scattered so thinly across such incomprehensibly vast distances that they almost never interact. The temperature of the universe approaches absolute zero. Entropy reaches its maximum. No gradients remain to drive any process. No work can be done. No information can be processed. No structure can form. This is heat death, the quiet, cold, permanent end of everything. Not an explosion, not a collapse, just the slow, inevitable triumph of the second law of thermodynamics, the universe whispering itself into stillness. And for 20 years, this was considered the most likely fate of the cosmos. The universe would expand forever, cool forever, and die the quietest death imaginable. But recent discoveries have complicated this picture in extraordinary ways. In 1998, two independent teams of astronomers discovered that the expansion of the universe is not slowing down, it is speeding up. Something is pushing space apart at an accelerating rate. They called it dark energy. It makes up 68% of the total energy content of the universe, and we have no idea what it actually is. This discovery won the Nobel Prize in Physics in 2011, and it opened the door to scenarios far more violent than heat death. If dark energy is constant, the universe expands forever, and heat death is the result. But what if dark energy is not constant? What if it changes over time?
If dark energy strengthens over time, a scenario involving so-called phantom energy, the expansion of the universe could become so extreme that it tears everything apart. Not just galaxies, not just stars and planets, atoms, subatomic particles, the very fabric of space-time itself. This is the Big Rip. And it has a timeline. If phantom energy is real, the Big Rip would unfold in stages. Roughly 60 million years before the end, gravity can no longer hold galaxy clusters together, and they fly apart. 3 months before the end, individual galaxies dissolve, their stars scattering like sparks. 30 minutes before the end, stars and planets are torn apart. 1 second before the end, atoms are ripped in half. And at the final moment, space-time itself is shredded beyond repair. The universe does not fade, it is destroyed, from the largest structures down to the smallest, in a cascade of violence that takes less than a cosmic heartbeat. The Big Rip would occur in a finite time, perhaps 20 to 30 billion years from now. It is not the most likely scenario, but it is the most dramatic. But here is what makes this subject suddenly, urgently relevant. In 2024, new data from the Dark Energy Spectroscopic Instrument, DESI, the most ambitious galaxy survey ever conducted, revealed something unexpected. Dark energy might not be constant after all. The data suggests that dark energy may be weakening over time. And if dark energy weakens enough, or even reverses sign from positive to negative, then expansion could eventually stop and reverse. In October 2025, physicist Henry Tai at Cornell University published a paper in the Journal of Cosmology and Astroparticle Physics proposing exactly this. Based on the DESI data, Tai calculated that the cosmological constant may actually be negative.
If true, the universe will not expand forever. It will reach a maximum size, stop, and begin contracting. Everything that has been flying apart for 13.8 billion years will start falling back together. Temperatures will rise, density will increase, and in roughly 20 billion years, the universe will collapse back into a state resembling the Big Bang, a big crunch. This is the cosmic mirror image of the beginning, a return to fire. I have to be clear about the state of the science here. The DESI data is new. The interpretation is preliminary. Most cosmologists still favor heat death as the most likely outcome. But the possibility that the universe could end not in ice, but in fire, that everything could collapse back into itself in a finite and relatively short time, is now a live scientific hypothesis backed by real observational data. That is extraordinary. And then there is perhaps the most unsettling scenario of all: vacuum decay. Quantum field theory tells us that our universe exists in a particular energy state called the vacuum state. But what if our vacuum state is not the lowest possible one? What if it is a false vacuum, a temporarily stable state that could, at any time, quantum tunnel into a lower energy true vacuum? If this happened, a bubble of true vacuum would form at some random point in space. The laws of physics inside the bubble would be different from the laws outside, and the bubble would expand outward at the speed of light, destroying everything it touches: stars, planets, atoms, the fabric of space-time itself, all converted into a new state of reality governed by different physics. A wall of destruction expanding at light speed that you would never see coming and could never escape.
And this could happen at any time, tomorrow, 1 billion years from now. It might already be happening somewhere in the universe, the bubble racing toward us at the speed of light, and we would have no warning. You would not see it approach, you would not feel it arrive. One moment the universe is as it has always been. The next moment, everything within the bubble obeys different laws, different physics, different reality. And the old reality, our reality, is gone. In May 2025, researchers published a new paper extending Hawking's black hole evaporation idea to all massive objects. They showed that not just black holes, but white dwarfs and neutron stars could also slowly evaporate through a Hawking-like process called gravitational pair production. Their calculations suggest that the last stellar remnants might decay in roughly 10 to the 78th power years, far sooner than the old estimate of 10 to the 1100th power years. The universe might be dying faster than we thought. Not dramatically, not violently, but the ticking clock is running quicker than previous models predicted. I want to be honest about how this makes me feel. Vacuum decay is the one scenario that I find genuinely terrifying, not because of the destruction, because of the randomness. It is not earned, it is not the result of entropy or time or any comprehensible process. It is a dice roll, a quantum fluctuation. The universe could simply switch off at any moment for no reason, and there would be nothing anyone could do about it. But before despair sets in, let me offer some perspective. Heat death will not happen for a googol years. The Big Rip, if it happens at all, is at least 20 billion years away. The Big Crunch, if Ty's paper is correct, is also roughly 20 billion years in the future. Vacuum decay, while theoretically possible, might never happen. And the standard model of physics actually suggests our vacuum is likely stable, or at worst, very long-lived. And proton decay has never been observed, despite decades of searching. The universe is not dying tomorrow. It is not dying in our lifetimes, or our species' lifetime, or our sun's lifetime. We have time, enormous amounts of time, more time than we could ever use. And I think this is where the real lesson lives, not in the death, in the contrast. Right now, in this thin sliver of cosmic time called the Stelliferous Era, the universe is doing something extraordinary. It is making stars, billions of them, and around those stars, planets, and on at least one of those planets, life, conscious, curious, questioning life that has figured out how the universe began, how it will end,
and has the audacity to feel something about it. We exist in the only era when looking up at the night sky produces something other than darkness. We exist in the only era when fusion reactions in stellar cores produce the heavy elements needed for chemistry, for biology, for thought. We exist in the only era when it is possible to ask how the universe will die and have the tools to answer the question. The Stelliferous Era is a brief, bright window. Before it, the universe was a featureless plasma. After it, the universe will be a featureless void. And we are here, right in the middle of the light, aware of it, grateful for it, unable to stop it from ending, but able to witness it while it lasts. Everything dies.
Stars, planets, galaxies, black holes, matter itself. But not yet, not for a very, very long time. And in the meantime, the universe is here. The stars are burning. The light is still on. And maybe that is the point. Maybe the universe does not owe us permanence. Maybe the beauty of the Stelliferous Era is inseparable from the fact that it ends. A sunset is beautiful precisely because it does not last. A life is precious precisely because it is finite. And a universe that burns bright for 100 trillion years before fading into eternal darkness is not a tragedy. It is the most magnificent thing that has ever happened. The fact that it happens at all, that matter organizes itself into stars and planets and beings capable of wondering why, that is not diminished by the fact that it will one day stop. If anything, it is made more extraordinary. The universe will die, but right now it is alive, and so are you. And you are made of the same atoms that were forged in the first generation of stars, atoms that have been part of gas clouds, supernova remnants, planets, oceans, and now you. You are the universe experiencing itself. And for a brief, bright moment in cosmic time, that is enough. If this video changed how you think about time, even a little, hit subscribe. We ask the questions that keep you up at night, every single week. Next time, what is inside a black hole, and what happens to you if you fall in? See you there.